Hi, everyone, and welcome back to Psych 4100 Cognitive Psychology for part one of chapter six. And chapter six is going to cover the structure of long term memory. So let's sort of reorient ourselves a little bit to what long term memory is. It's the giant storehouse of information that allows you to remember things from the moderate to long term past. Right? So this is anything beyond what we would define as short term memory. Now, in this part, in chapter six, we're not going to get into too many details about the how or the why of long term memory. We're going to spend a little bit more time on the what, the structure, just kind of what is long term memory, so that later in chapters 7 and 8, we can figure out how and why certain things are remembered and other things are not remembered. So, some of the questions that we will be able to consider during this chapter and after this chapter are things like, how does brain damage affect the ability to remember the past and or to form new memories? How are memories for personal experiences, like what you did last summer, different from memories for facts or just knowledge, like information like the capital of your state? How do different types of memory interact in our everyday experiences? And maybe are there some truths or myths to how memory loss has been depicted in the real world in things like popular film? Right? Can we, after we learn some things about long term memory, can we see perhaps some inconsistencies in the way memory is depicted in the real world? So, again, what is long term memory? Long term memory is just this archive of information. It's the big storehouse, it's the vault where you keep all of this knowledge that you've learned and all of your memories about past events. It's going to work closely with working memory, as working memory can go in and retrieve long term memories to put them in the conscious mind or in working memory so that you can incorporate that old information and knowledge into your current experience and future experiences. The storage of long term memory stretches just from really the moment something enters long term memory, which can be, just a few seconds, right? If you've been given a bit of information and you maybe study it and rehearse it, and you can get it into long term memory, in, I don't know, 5 seconds, 10 seconds, and you might be able to remember that bit of information forever. And that memory can exist for the rest of your life. Right? Think about some of the most memorable moments in your life, and you will remember them most likely forever. And one of the interesting facts about long term memory we'll discuss in a little bit of detail is, of course, that these memories that you have stored for years and years or decades and decades are subject to degradation. They're subject to change. Some of the details start to be not as clear or obvious or correct. We will return to this point in particular in chapter 8 when we discuss the errors of long-term memory. So again, long-term memory stretches from, give or take 30 seconds ago, basically just the border between something being in short-term memory versus it's no longer in your conscious mind, but you can still recall it. So, for example, what did you have for breakfast this morning would be a piece of information that's in long-term memory, because you're not actively thinking about it unless, of course, you are currently eating breakfast. And you might have gotten done eating breakfast 30 seconds ago or 20 seconds ago. But in the interim, you stopped thinking about breakfast. And when you stopped thinking about breakfast, that information was lost out of short-term memory, but it still existed in long-term memory. And of course, long-term memories begin at this moment when we cross over from short-term to long-term, and they can exist for the entirety of your life. We discussed these sort of control processes a little bit previously, but here we'll begin to elaborate on them across the next 2 to 3 chapters. The first, of course, is encoding. That's where we put something into long-term memory. We take a piece of information, it's in our conscious mind, it's in short-term memory. We do stuff with it, we think about it, we rehearse it, we deal with it, and in that process of dealing with the information in conscious mind, we encode it, we put it into long-term memory. We can then store and solidify that memory as a representation. And the better that we do this, the more likely we are to remember that piece of information in the future. And we'll talk about some of the things that can happen or not happen that can manipulate the sort of strength, if you will, of the storage of that representation. And then, of course, we have retrieval, which is just taking it back out of the long-term storehouse, putting it back into short-term or working memory so that we can access the information and do something with it. So we're back to our workbench and our storehouse, our safe analogy. We can encode information, which is moving it from short-term to working memory. Then we can store the information in long-term memory for long-term storage, and then we can retrieve it and put it back into the conscious mind. So one of the first things that we have to do as cognitive psychologists is prove that there's a difference between short-term and long-term memory, right? We can sit back and ponder and philosophize about these things all day long, but you need to have some evidence that there is a system of short-term memory and it differs from a system of long-term memory. One of the earliest and also the most simple ways that we can establish that difference is known as the serial position curve. This was really first done back in the early 60s. And let me take a second to explain the experiment because it is really, really important, both in the history of cognitive psychology and for our current knowledge of short-term and long-term memory. So what serial position refers to, if we look over here at this figure on the right, serial position refers to the location of a word in a list of words. So 0 to 5, right, are the first 5 words in the list, right? The first word, the second word, the third word, the fourth word, the 5th word in the list. And then so on and so forth. This would be the 6th word, the 7th word, the 8th word, the 9th word, the 10th word of the list, all the way to 20 words. So we have a list of 20 words, and we're considering each word based upon whether it's at the front of the list, the middle of the list, or the end of the list. And the procedure is very simple. You give people this list of words, and you have them, read and rehearse the words and try to remember as many of the words as possible. So of these 20 words, people get a couple minutes to study them, and then they have to write down as many as they can remember. Our y-axis is the frequency of correct recall. So the percentage of correct recall at each position in the list from the first word to the 20th word. So we'll notice that anything that's high on this graph gets remembered well. Anything low on this graph gets remembered poorly. And we can see a definite pattern here. We have this U-shaped pattern such that words in the middle of the list, so really kind of 5 to 15, are remembered very poorly, right? They're they're around, 20 to 30 to 40% correct. So we'll just call it 30% correct. That's items in the middle of the list. Items at the beginning of the list fare better. They get recalled better, although slightly better, maybe not dramatically better. And then items at the end of the list are remembered the best. And they're remembered incredibly well, right? Think about if you're reading a list of 20 words and you get to the end of 20, well, you sure as hell better remember the last one, right? You just saw it. And so, in fact, that's what we find, right? People are really good at remembering the last 3 or 4 of these words that were on the list because those were the most recent words that they saw. And so, what this effect really is the result of is 2 separate effects. The primacy effect, which is the idea that we remember the words at the beginning of the list better, and then the recency effect, which means we remember the words at the end of the list better, the most recent words versus the primary or the first words, and then everything in the middle has very low performance. So we get this cool effect. Right? Words at the beginning are remembered better, words at the end are remembered better, words in the middle are remembered least well. As sort of maybe a helpful way that you can use this in your real life is that if you're engaging in something for which you want to be remembered, you should go first or you should go last. So if you have to sign up for a job interview time slot, and you can sign up for any hour between 9 a.m. and 5 p.m., you should not sign up for noon or 1. You should sign up for 9 a.m. or you should sign up for 4 or 5 p.m. because the interviewers are going to be more likely to remember you if you went first or if you went last. Okay, so how does this help us? What does this tell us about long-term memory? Well, the primacy effect, the idea that the words at the beginning are remembered better, and here's just a replication of the serial position curve from 1971. They get this experiment by Rundus actually got a little bit more of a dramatic U-shaped where they got more of a primacy effect as well. So we really get a U-shape here as opposed to this kind of U-shaped from Murdoch. Interestingly, the primacy effect seems to be due to rehearsal. So the red bars are memory, right? Percentage recalled. The blue dotted bars, or line rather, the blue dotted line is the number of times that word was rehearsed or said out loud by the participant. So we can see that memory and rehearsal track each other very closely at the beginning of the list. Why is this happening? Because the more you rehearse a word, the more likely you are to encode it and store it into long-term memory. Think about remembering someone's phone number, right? You rehearse, and what you're doing is you're shoving it into long-term memory with that rehearsal process. So words at the beginning of a list have more opportunities to be rehearsed because they're at the beginning. You see them, right, for long, or you saw them first. So you get to engage with them for a longer amount of time. So you rehearse them more, and so you remember them better because you got them into long-term memory with that rehearsal. But notice that the recency effect, the better memory for words at the end of a list, has no relationship with rehearsal, because by the time you get to the end of a 20-word list, you can't rehearse all 20 words. It's impossible, right? Your phonological loop does not have that much capacity. You can't repeat them fast enough to rehearse all 20 words. But the recency effect still exists, even though you're not actually rehearsing those words. So what that means is that the primacy effect is due to rehearsal and long-term memory encoding and storage, whereas the recency effect is due to the existence of those items still in short-term memory, right? Remember, short-term memory can hold things for 15, 20, 30 seconds. So the items at the end of the list, the most recently presented items, are still in short-term memory, so you can recall them easily. And the items at the beginning of the list had enough time for rehearsal to get into long-term memory. And the items in the middle just don't get remembered because they have no advantage. So the primacy effect shows us the existence of rehearsal and long-term memory, and the recency effect shows us the existence of short-term memory. And interestingly, in 1966, we have another experiment kind of on this same topic, where if you force people into a 30-second delay from giving you the words that they remember, from recalling the words, if you force people to wait 30 seconds after the list is over and then start recalling the words, then the recency effect disappears because the words are no longer recent because we've waited 30 seconds and now they're out of short-term memory. And so you don't remember those words at all, but you still remember the primary words, the first words, because they're not dependent upon short-term memory. They're dependent upon long-term memory. So the serial position curve, or the serial position effect, which is a combination of the primacy and recency effects, shows us that yes, in fact, short-term and long-term memory are separate systems with separable properties, and we can dissociate them from one another experimentally. We can also dissociate short-term and long-term memory from neuroscience and neurocognitive experiments with individuals with brain damage. So 3 of the most famous patients in all of neuroscience are HM, Clive Waring, who is recently alive. I believe he passed away maybe just in the last decade or so. Don't quote me on that. But he was alive recently enough to have some actual documentary footage of Clive exist. And then KF, who's another patient. All 3 of these individuals had some form of brain damage. HM and Clive had damage to their hippocampus. HM had his hippocampus removed in order to combat these debilitating seizures that he was having. I believe Clive had his hippocampus damaged during a stroke. And then KF had a different part of his brain, not his hippocampus, but a different part of his brain damaged in, I believe, a motorcycle accident. Now, what's special about these 3 patients is that they showed dissociation between the effects of their brain damage on short-term versus long-term memory. So HM and Clive, who had damage to the hippocampus, were perfectly fine with short-term memory. They could hold a conversation with you in the moment. They could talk about, the ball game on TV. They could talk about, the cat outside. That they can, anything that's in conscious awareness, they're fine. They can hold that immediate conversation. But they had problems creating long-term memories. So basically taking that information that's in conscious awareness and encoding it and storing it into long-term memory. Basically, from the moment of their injuries, they could no longer create new explicit long-term memories. So if you went to visit Clive, he would seem like a perfectly, maybe not perfectly, he would seem like a somewhat normal older gentleman. You could have a cup of tea, you could watch some TV, you could talk about the weather, right? Whatever, it seems okay. And then if you came back the next day, he would have no memory that you were there the day before. because he is unable to take the information in short-term memory and move it into long-term memory. So he would behave, HM and Clive behave much like dementia or Alzheimer's patients. KF had the opposite impairment. His long-term memory was fine. He could create new long-term memories and remember his previous long-term memories, but his short-term memory was impaired. He had trouble keeping things in mind in the moment. So what this shows us is a double dissociation between short-term and long-term memory from different areas of brain damage, which, along with the serial position curve, strongly suggests a neurological basis for the difference between short-term or working and long-term memory. Okay, so this is what I just said. Oh, sorry. So yeah, so HM as well as Clive had damage or removal of the hippocampus. KF had damage to his parietal lobe. So that's sort of by your the top of your head, right? That's the motor cortex, if you will. So the very top of your head is where your parietal lobe is. Okay. The next thing we're going to talk about, so we've established that short-term and long-term memory are in fact different separable systems based in different parts of the brain. The next thing we need to worry about is the different ways that we can code or encode information in both short-term and long-term memory. Because in fact, we can code information in three different ways: visual, auditory, and semantic encoding. Visual is just like it sounds. It's your memory for images. Auditory is your memory for sounds. Semantic is a little more difficult. It's not obvious what that means from its name. Semantic is just meaning, so ideas, essentially. So for example, you all probably remember that George Washington is the first president of the United States. That's a semantic memory. It's a piece of information that's not bound to any physical structure. It's just knowledge. Versus your memory of, and what could be an auditory memory, your memory of the chorus, the way the chorus sounds from your favorite song, or your memory of the sound of the barking of your dog, right? Your particular dog has a particular bark, and you know what it sounds like. That's an auditory memory. It's a memory tied to a physical thing in the world, right? A sound, a noise, an actual entity in the world. It's not just an idea. It's not just data or information or knowledge. It's a thing in the world. And of course, visual is a little more easy. You know, what does your mom's face look like? What does the front door of your house look like? You know, what color can you visualize your first car, right? Those sorts of things. Again, memory for information that's tied to a physical thing in the world that's visual. So we have some interesting evidence for the way we code things in long-term memory. It comes from Wickens and colleagues in 1976. So we have two groups of participants. Group A basically gets a series of lists of fruit, and they have to remember each list of fruit, right? So banana, peach, apple, right? How long can you remember that for? Plum, apricot, lime, how long can you remember that for? And then we have group B, who get the same 4 trials, but their first 3 trials, they're trying to remember professions: lawyer, firefighter, teacher. Then dancer, minister, executive. Then grocer, doctor, editor. And then they get switched up in trial 4, and they get fruits. So notice that for group A, the content of their trials is consistent across all 4 trials. Whereas in group B, the content of their trials shifts. It's consistent for 3, and then it changes with trial 4. So what happens? Well, for the group A that gets fruits, we see that performance declines over time, and this is called proactive interference. Basically, the earlier information, the fruits, is interfering with your ability to remember each subsequent list of fruits. So the proactive information, the first information, interferes with your ability to remember similar information that comes next. Basically, it's easy to get all these fruits confused because they all belong to the same category, right? They're all similar in kind and nature to one another. And so it would be very easy to sort of misremember certain fruits as being in certain trials, right? That'd be super easy to do, to get them all mixed up. And so that's what we see. Memory for the first trial is really good, and then people start to get mixed up because all the fruits start sounding the same. Versus group B, who get professions, fruits. We see a similar pattern from trial 1 to 2 to 3. We see proactive interference for the professions. But then in their fourth trial, where they get a switch, now they get different information. They get fruits. They get released from that proactive interference. It doesn't impact them anymore because fruits are not similar to the professions from the first 3 trials. And so memory increases again. So this tells us something interesting, which is that we code in short-term memory using sort of the meaning of the words, and in this particular case, their category identities. That things that are similar in kind to one another can get confused with each other, but things that are dissimilar with each other are more likely to be remembered independently and better. So this is called semantic coding. And of course, this is going to happen in long-term memory as well. In short-term memory, this semantic coding tends to be more sort of exact and defined and detailed. Whereas in long-term memory, we start to get maybe some degradation of the semantic memories, where we don't remember the exact details, but we remember the general meaning behind things. So one way we know this is that there's a difference between recall and recognition. So recall would be if I asked you for a short answer question on an exam. So here's a term. What is its definition? Right? And it's just an open blank, and you have to recall the definition. That's recall for semantic information. And that can be difficult in long-term memory because it's tough to remember all of those details. But what's easier is actually recognition memory, which is simply identifying a previously encountered stimulus. That's not a free response question. That's a multiple choice question. Because in a multiple choice question, the answer's there. You know that the answer is either A, B, C, D, or E, right? And if you can just recognize the correct answer, it's much easier than recalling the answer. So in long-term memory, this semantic coding can start to degrade such that recall becomes difficult, but recognition memory remains high. It's easier to recognize a previously seen piece of information than it is to recall that information sort of on its own out of the blue. One good example of this is a very simple experiment, Sachs in 1967, where they asked participants to read a passage, right, and then recall the passage at some later point. And, as is kind of obviously the case, it's very difficult. If I gave you a book to read, right, and it's, let's say, a 200-page novel, in no way, shape, or form are you going to be able to recall exactly every word, every sentence of that novel in a row in order. Right? It's impossible. It's ridiculous to assume or to think that you could perfectly recall a 200-page book. But you could give me a synopsis in your own words, couldn't you? Right? You could give me the gist of your memory for that book. And so what that tells us is that semantic coding and long-term memory often takes an inexact form. You remember the meaning or the gist, the general idea of things, and the details start to get fuzzy. The exact details start to fade, but your memory for the general concept, the general idea, remains strong. And in fact, we're going to find that this comes into play a lot in when people make errors of memory, because people will be able to get the general idea right, and then they'll start to make errors in the details. And so, of course, we can think about there being differences in the way that we code these three types of information in short-term versus long-term memory. So we can have visual short-term and visual long-term memories, auditory short-term and auditory long-term memories, and semantic short-term versus semantic long-term memories. Okay. So that's the basics of how does long-term memory differ from short-term memory, and how can we sort of get information. What does information look like in short-term versus long-term memory? Now what we're going to do is break down the divisions of long-term memory, because, yes, it gets even more complicated. Long-term memory is not just one thing. Long-term memory can be split into two major categories. Explicit memories, which is generally what we think of as memory in day-to-day life. So when you're with your friends or your family and you talk about having a memory, you're talking about an explicit, conscious memory. Either it's an episodic memory, so of a personal event, your 16th birthday party, what you had for breakfast yesterday, your first kiss, right? Whatever, some personal event in your life. That's called an explicit episodic memory. Only you possess that memory because it's an experience that you had for yourself from your perspective in your life. That's an episodic memory. An explicit semantic memory is just knowledge or facts. So George Washington was the first president of the United States. You don't remember him being the first president of the United States. You don't have an episodic memory of him, but you know the fact. You have the knowledge. Another good example I like to use is from my own life. So it's semantic knowledge that the Atlanta Braves won the 1996 World Series. If you didn't know that, now you do. But that's just a fact, right? You could read it in an encyclopedia. It's a piece of trivia knowledge that the Atlanta Braves won the 1996 World Series. But I have an episodic memory from that, which is that I was watching the deciding Game 6 at my grandmother's house, and when I believe it was a pop-up down the third base line. I might have that detail wrong, but I believe it was a pop-up down the third base line that was the final out. I remember when they won, when that final out happened, I was jumping up and down on my grandmother's couch. She got really mad at me for doing this and snatched me down off the couch by my ear. and scolded me. But then she felt bad, and the next day when she went out to run some errands, she brought me back like an Atlanta Braves World Series champion baseball hat to say that she was sorry, and it was one of my treasured things that I had in my childhood for quite a few years. So see, that's an episodic memory that only I possess. Only I have that memory of that event. But we can all share the semantic knowledge of the 1996 World Series champion Atlanta Braves. Another piece of useless knowledge, Atlanta Braves center fielder Andrew Jones became the youngest player in history, and I believe is still the youngest player in history to hit a home run in the World Series at, I think he was 19, not even 20 years old when he hit a home run in that World Series. Okay, so the other major part of long-term memory is implicit memory. This is a little more difficult. It's not exactly what you usually think of as being memories, but these are made up of procedural memories. So memories for um, things like playing the guitar, performing an action in sports, riding a bike. If you're a chef, then you have procedural memory for how to chop things in certain ways, how slicing a cucumber versus chopping a cucumber or an onion, and your body just remembers how to do it, right? If you do something enough times, your body remembers. It's a memory, right? But it's not an explicit memory. It's not a conscious memory. It's a non-conscious or an implicit memory. So procedures like playing an instrument, playing a sport, doing a repetitive action like chopping, how to drive a car, how to ride a bike, those sorts of things. Priming is also considered a type of memory. So, for example, if I primed you with the color red, and then I asked you to start naming fruits, you're more likely to say things like cherry or strawberry or apple than if I primed you with the color orange, you're more likely to say, fruits like an orange or a nectarine or a mango. And then conditioning, this is just classical and operant conditioning, right? Skinner and Watson and Pavlov, those are also considered implicit non-conscious memories. So it's easy to see how explicit memories are memories because that sort of fits with your personal experience in the world of the types of things that are memories. People don't usually consider in their day-to-day lives these things on the right, these implicit memories, to be memories. But remember from chapter 5 our really, really, really broad definition of memory, which is any time information from the past impacts you currently or in the future. Right? Any time information from the past impacts you currently or in the future, that's a memory. And so implicit memories fit that definition as well. So these episodic memories, so we'll start with explicit episodic memories, involve what's called mental time travel. And interestingly, this is sort of the element of cognition that allows you to imagine the future, sort of travel into the future, and maybe plan or consider what you might do or how you might act in a situation in the future, as well as remember the past, and sort of travel back in time to what your grandmother's kitchen smelled like on a Sunday afternoon while she was cooking, right? Versus semantic memory, which does not involve traveling forward or backwards in time. It just involves knowing things about knowledge and facts. So this idea of mental time travel seems kind of weird, but in fact, this might actually be the reason we have memory. Our memory systems likely co-evolved with this ability to project ourselves into the future to plan. So planning is critical for survival, and we have to take information from the past in order to plan for the future and survive. So, for example, remembering weather patterns or the changes of seasons, or if you're a hunter gatherer, the movement and migration of animals, or when does the river flood and when is the river dry. These sorts of cyclical changes are the exact pieces of past information that we need to use in order to project and plan for the future in order to survive. And so it's thought that this system of the past and the future and our ability to sort of move our conscious self fluidly between the present, the future, and the past sort of all co-evolved as this one system in cognition to help with survival. And in fact, we see that the memory or the areas of the brain involved in memory about remembering the past and projecting into the future, so the left image and the right image, are basically the same brain areas. The same areas of the brain are used when you remember the past and when you project into the future. And interestingly, a couple of our patients from neuroscience who had episodic memory loss also had trouble imagining and describing the future. So it's highly likely that these two abilities really are one big system. We just don't typically think about them that way. But anytime you're hypothesizing about the future, you're actually using the same memory system that you use to remember the past. And just here's some more evidence. The blue bars are remembering the past. The green bars are projecting to the future. Notice how at each of these areas of the brain that are circled, right here, right? Each of these brain scans has an area that's circled, and then the data for that area are shown to the right. Notice how the green and the blue bars always go together. Right? They're always similar to one another in direction and magnitude. And so this suggests that, again, remembering the past and orienting to the future are essentially the same process. Okay. We also have good evidence that semantic and episodic memories are dissociated. KC helps us out again here, as well as sort of an unnamed Italian woman with some brain damage. KC was perfectly capable of remembering information, semantic information, but he couldn't form new episodic memories. And this unnamed Italian woman had the exact opposite, the dissociated effect. She was perfectly fine with creating and remembering things about herself, but she had difficulty creating and remembering facts, semantic information. So the distinction between semantic and episodic is not academic, it is real, and it's based in the brain. So here we can see that the blue areas of the brain, so this is a little bit of a fuzzy image, sorry, it's from kind of an old paper. Doesn't say, I'm forgetting when this was published, 2004. So a bit of an old paper, the early days of fMRI in neuroscience. This at the top is the front of the face, the front of the brain. This is the back. The blue areas are areas of the brain that activate when we're engaging semantic memories, so just knowledge and facts. And the orange and yellow areas of the brain are the areas engaged in episodic memories. So this explicit memory sort of system, this arm of long-term memory, really does have these two distinct neurological processes for remembering things about yourself and remembering facts and information. Interestingly, and this probably happens a lot to us and is responsible for, again, some of the typical memory errors that we see in day-to-day life, is that something can start as an episodic memory and then it starts to fade, and what you're left with is only the semantic information. So I want you to imagine someone who their first autobiographical, that's what these are called, these autobiographical memories of their own experience, is going to Six Flags, going to a theme park and riding their first ride. It was just such an amazing, exciting moment. It's ingrained in their brain forever, and they could describe to you the weather. They can describe the colors, the sights, the sounds, the cotton candy they ate, who was there, all this amazing stuff, and they can close their eyes and they can re-experience it. Right? It's an episodic autobiographical memory. Over time, let's say that person is now 50, 60, 70, 80 years old, they might actually lose those episodic details and be left with just the semantic knowledge that, yeah, when I was little, I went to Six Flags with my family one time and it was awesome. Right? That's all I remember. Notice how also they're losing the details. They're remembering just the gist, the general idea. And that general idea means they've lost these autobiographical details and they're left with what's called a personal semantic memory. Just the knowledge that when I was 5, I went to Six Flags. And often what happens is that people don't realize this has happened. People's autobiographical memory has faded to a personal semantic memory. So what they're left with is just the general knowledge and the general idea. And they've lost the details, but maybe they start to make up the details, right? The details get kind of fuzzy. They start to get some memory errors, some false memories, because they're trying to fill in the gaps and fill in the parts they've lost. And then that memory can change over time. This is a really big problem with the legal system and eyewitness accounts and eyewitness memory. And we'll talk about that in detail in chapter 8. Okay, so here's just a quick little figure to help us keep episodic, semantic, and autobiographical memories straight with their definitions and some examples. Okay, so that's a good stopping point for part 1 of chapter 6. We will pick this up with part 2 and finish the lecture for chapter 6 on long-term memory structure. Thanks, everybody, and I will talk to you next time.